Good day everyone. In this video we will be looking at a concept called cumulative distribution function, or otherwise known as CDF. Alright, so by the end of this video you should be able to define the cumulative distribution function of a discrete random variable. You should also be able to represent it using a formula or graph, and you should also be able to calculate probability using this cumulative distribution function or using PMF. Alright, so the word cumulative is, if you think about it, you know that it's synonymous with words such as increasing or increasing quantity, or words such as accumulative, accumulating, growing, adding or additions. So we would like to define a probability function that calculates the probability that the observed value of a random variable x will be at most some particular x value or some particular numerical value. So we would like to define a function that calculates this probability right here. Let us firstly consider or look at the PMF in example 3.7. So the example in 3.7 was based on the number of defectives, or random variable x looked at the number of defectives in a randomly selected container. We had 6 containers, and each container had different number of defectives, right? So at the end we concluded that possible values of x would be 0, 1, and 2 with these probabilities here. And since this is a valid PMF, we know that all probabilities for the possible values of random variable x will be positive, right? That's the condition. Px is greater or equal to 0 for all x. And if we add up all the probabilities, we see that it will add up to a total probability of 1. Alright, so now let us say we want to calculate the probability that x is at most 1. Alright, so which values of our random variable x fits this criteria here of being less than or equal to 1? So if we look at the possible values of x, which is 0, 1, and 2, which of these values are less than or equal to 1? We see that it's x equal to 0 and 1, right? So this probability of x being at most 1 can be calculated as P0 plus P1, and that is equal to 0.5 plus 0.167, that is equal to 0.667. Okay, good. Now the probability that x is at most 2, that is capital P bracket x less than or equal to 2. At most, that's the key word, meaning it's any other possible value that is less than 2, including 2. So 2 is the threshold or the maximum value that we're looking at here. Okay, so in this case, if you think about it, which possible values of our random variable x are less than or equal to 2, we see that it's all values, x equal to 0, 1, and 2, right? And so in this case, the probability is equal to P0 plus P1 plus P2, and that is equal to 0.5 plus 0.167 plus 0.333. If you add them all up, it will give a total probability of 1. Very good. Okay, so now let us say we want to get a general formula to calculate the probability that x is at most 1, or x is at most 2, or x is at most 3, or 4, or 5, or any other particular value, right? What is the probability that x is at most 7? If you're looking at insurance claims, what's the probability that you'll have at most 7 or 10 claims this month? Or what's the probability that we have at most 10 people that will react or get an allergic reaction to some drug, right? So we're interested in finding the general formula or probabilities that will help us calculate or let us know what is the probability that x is at most some particular value. Cool. So now the definition says the cumulative distribution function, abbreviated using the letter CDF, is denoted by capital Fx. So the CDF of a discrete random variable x with PMFPX is defined for every number. So for every number x by this function here. So fx is equal to the probability that x is at most this particular value there. And that is equal to the sum of the probabilities up until that specific x value. So for any number x, fx is the probability that the observed value of x will be at most x. All right? Makes sense? Good. So what are the general properties of a CDF, of a discrete random variable? So the 4 general properties is that the CDF fx is a non-decreasing function. We will have a look at what that means. And the CDF fx will have a minimum value of 0. So fx is greater or equal to 0 and less than or equal to 1. This makes sense because fx calculates probability, right? And we know that probability is always between 0 and 1, including 0 and also including 1. It's always between 0 and 1. You'll never have probability of 1.2 or negative 16. No. Point 3, if x-min is the minimum or the smallest possible value for a random variable x, then fx-min is just equal to the probability that x is equal to that smallest value. So for example, if we have possible values of random variable x as 0, 1, and 2, like we saw in the previous example, then the probability that x is less than or equal to 0 will just be the probability that x is equal to 0. Do you agree? Since if you think about it, which possible values of x fit this criteria? Which possible value of x is less than or equal to 0? We see that in this example, it's only 0. So we have probability that x is equal to 0. All right? Okay, now the 4th point, if x max is the maximum or largest possible value for random variable x, then f of x max will then be equal to 1. Does it make sense? So if we look at this example again, probability that x is less than or equal to 2 is equal to p0 plus p1 plus p2, and that is equal to total probability of 1. Since 2 is the largest or maximum possible value for a random variable x in this example, or in example 3.7. Okay, does it make sense? Yes. Good. So now this concept of a non-decreasing function, what does it mean? So it means that let's say, suppose that x equal to x1, x2, and x3 are possible values of random variable x. Where x1 is less than x2, is less than x3. Okay. So if x is a non-decreasing function, if for x1 less than x2, we have that if x1 is less than equal to fx2. So if x1 is less than x2, then the probability that x is less than x1 will be smaller than the probability that x is less than or equal to x2. Does it make sense? Right? So if you look at the previous example, the probability that x is less than 1, less than or equal to 1, is equal to 0.667. And that probability is less than, this probability is less than the probability that x is less than or equal to 2. Alright? Where that probability there is 1. So 0.667, we see that it's less than the probability of 1. Now how can we prove it? Okay, so if we start with fx2, we know that fx2 is equal to the probability that x is less than or equal to x2 by definition, right? By definition of CDF. Now, if we think about all the possible values of x that fit this criteria here, which values of x are less than or equal to x2? Which one? So we know that x1 is included in this criteria here, right? Okay, so we will say that this is equal to the probability that x is less than equal to x1 union with probability union with any x value that is between x1 and x2 if there are any, right? So now this is equal to probability that x is less than equal to x1 plus the probability that x is greater than x1 less than equal to x2. And by definition, we know that this probability here is equal to f of x1, then plus probability of x1 being, or x greater than x1 less than equal to x2. So at the end, we know that f x2 is equal to f x1 plus a little bit of some probability, which is a positive value. And so this means, or it implies that fx2, it's greater, I'll say greater equal to fx1. Does it make sense? Since fx2 is made up of two components, fx1 itself and some other probability. And so fx2 will then just be greater than fx1. Make sense? Right. So we will say that, so if then x1 is less than x2, it implies that fx1 is less than equal to fx2, or fx2 is greater equal to fx1. Okay, so that is what it's meant by a non-decreasing function. Okay, and then we have a proposition in section 3.2, the first proposition, which says for any two numbers a and b, where a is less than equal to b, the probability of x being greater equal to a less than equal to b is equal to f of b minus f of a minus, where f of a minus represents the maximum of the cumulative probability values to the left of a. Equivalently, if a is the limit of values of x approaching from the left, then f of a minus is the limiting value of our CDF fx. So if you have here possible values that are only integers, where we have possible values a and a plus 1, a plus 2, a plus 3, a plus 4 up until some maximum value b, then the probability that x is between a and b, including a, including b, is equal to the probability of x being less than or equal to b minus probability of x being less than or equal to a minus 1. Alright, so let us see what is meant by that. So if we look at the proposition on the left hand side, and suppose that we have a scenario on the right hand side where x has possible values 0, 1, 2, 3, 4, 5, 6, and 7, and we have the corresponding probability values for each of these possible values. We will assume that this table here gives us a valid PMF, or probability distribution function, right? Or probability mass function. So let's say, for example, we are looking at probability, or calculating the probability that x is greater equal to 2 but less than equal to 5. Now, if we firstly look at the PMF, we will have to look and see which x values are between 2 and 5, including 2 and including 5. So these are x values 2, 3, 4, and 5, right? So out of all the possible values for an variable x, the only x values that fit this criteria here between 2 and 5 is equal to 2, 3, 4, and 5. Now we can calculate this probability as probability that x is equal to 2 plus probability x equal to 3 plus probability x equal to 4 plus probability that x is equal to 5. Right? So that is just 0.03 plus that 0.13 plus 0.25 plus 0.39. All right. Else, we can calculate this probability using a CDF function if we have a CDF function. In this case, we do not have a CDF function, but if we did, then it will be the cumulative probability. So it will be everything, or the probability to the left of possible value x equal to 5, right? So it's the probability of x less than equal to 5. And then you subtract everything else that is less than the possible value or the minimum value here of 2. So we have probability of x is equal to 5 minus probability of x less than 2. That is equal to f of 5 minus probability of x is less than equal to 1, since that's the only x value that's less than 2. And so we have f of 5 minus f of 1. All right. Do you now understand this proposition here? So in this case, probability of x greater equal to 2 less than equal to 5. A here was 2, B here was 5. And so the formula of the proposition says it's equal to f of 5 minus f of 2 minus, so anything to the left of 2, the maximum value to the left of 2. And what is to the left of 2? It is possible value of 1. So minus f1. All right. And then this sentence here, if possible values are integers, in this case, we have a nice example where possible values is 1, 2, 3, 4, 5, 6, 7. All right. So it means that the probability that x is greater equal to 3 less than equal to 6, that is equal to f of 6 minus f of the next integer, or the maximum value to the left of 3 or just below 3, and that is, or the left hand side value, that is 2, right? So minus f of 2. So that is equal to probability of x less than equal to 6 minus probability of x less than equal to 2. Do you understand? All right. So have a look again if you do not understand. All right. So that is the proposition. Now the three ways to represent the CDF of a discrete random variable. Either we can draw a table, or the one that you need to know how to do, the formula, as well as doing a graphical illustration called a step function. All right, so there are three ways. Either you can draw a table, or you can give a formula, or do a step function. In a test or exam, it will be clear to you. We will ask you directly, do a table or a formula, give a formula, or draw a step function. Okay, cool. So in the next video, then we will have a look at a couple of examples. Cool.